We do paid labor. We have customers that deploy our robots in their manufacturing facilities and their logistics facilities, and Digit works in a full shift and gets paid for it. So that's the real value of creating a human-centric robot like Digit. It's to be able to be flexible and easy to deploy in all of these different places in a process flow that were traditionally very difficult and specific. I would say if you are a humanoid robotics provider yourself, I would encourage you to understand safety and start, working with the standards bodies that are working on that.
Hi, Pras. Would you introduce yourself?
Hey, I'm Pras Velagapudi. I'm the Chief Technology Officer at Agility Robotics. And at Agility, we are working on building Digit, the humanoid that's made for work.
Hell yeah. Tell me about Digit and tell me how it's made for work.
Yeah, so Digit is our human-centric robotic platform. So it's a robot with 2 arms and 2 legs. It's spun out of technology coming out of Oregon State University and a bunch of related academic research around how to create a dynamically stable robot. And that evolved into the platform that we created, which is doing right now material handling. So moving around totes and bins and things like that in warehouses and logistics and manufacturing applications. And so we're building up a robot that's really intended not just to be a thing that looks kind of human-like, but something that actually can go into environments that are designed for humans, those parts of facilities, and do useful work. We do paid labor. We have customers that deploy our robots in their manufacturing facilities and their logistics facilities, and Digit works in a full shift and gets paid for it.
Awesome. And yeah, you just celebrated an anniversary of Digit working somewhere for a while. Would you tell me a bit about that?
Yeah. So we recently celebrated our 1-year anniversary being deployed at GXO. So GXO is a third-party logistics provider. So they do order fulfillment for a number of different customers. And one of them is Spanx. And Digit has been helping to do order fulfillment for Spanx orders at a facility in Georgia for just over a year now. We just crossed that boundary.
So what does that look like? Does it mean that Digit is working an 8-hour day, then taking a rest, or is it working continuously during the day, or how does it look for Digit to be deployed in this factory?
What it looks like,
warehouse.
A deployment looks a lot like Digit basically matching what the rest of the process can do. So in this particular facility, Digit's working a full shift because the things upstream and downstream of Digit, the other stations, are also working that same shift. So that's the limiting factor. In a facility where there were 2 shifts, Digit could also work 2 shifts. So in this particular facility, I think it's basically a single shift. I think it's roughly 8 hours. Digit basically starts up in the morning and starts doing work where essentially it's a part of the process where orders have been picked from some inventory upstream, and they arrive at a station on an AMR, an autonomous mobile robot that's carrying a bunch of different bins for the different orders. So Digit actually unloads those bins off of the AMR and puts them onto a conveyor so they can go to the next station, which is a packing station where they get packed to go out to customers. So it's one part of a process that interacts with automation on both sides. And I think that's really important, is that we're building Digit not to replace all automation in the facility, but really to work with the other types of things that are there. Like we have great automation for things like conveyance, and we have great automation for driving around a facility with an autonomous mobile robot. And then maybe not as great options when we're getting to a place where those 2 things interact and you're trying to get something from place to place. You're trying to go from a shelf to a conveyor, or a shelf to a mobile robot, or a mobile robot to a pallet that's going to go on a truck. Those are all places where you typically have to have higher cost, more customized automation that's built around what those other pieces are doing. So instead of doing that, we can have this single flexible platform that can go in and glue these other process flows together. And that's really the utility of a platform like Digit. We can come into a use case like that, and without reconfiguring everything, without bolting a bunch of additional stuff to your AMR or completely reconfiguring your conveyor and adding a big gantry robot or something like that, you can just connect these pieces together. And if you need to use Digit somewhere else in the facility, the same platform, same Digit unit can go over there and basically with more or less mostly software reconfiguration, go do other tasks in that other part of the facility.
Mm-hmm.
So that's the real value of creating a human-centric robot like Digit. It's to be able to be flexible and easy to deploy in all of these different places in a process flow that were traditionally very difficult and specific.
Mm-hmm. Very interesting. Yeah. So, I mean, there's a lot of questions around why humanoids, and I think that's a big answer to it in some sense, because what you're saying is that we have these systems that are highly optimized, but in the intersection or like in the boundary between them, it's harder. And so like people would do it, or you could have really complex, costly integrations that would be set up to make the systems map from one to the other. But the flexibility of the form factor makes it so you can kind of drop them in and they can do the task, and it's a software change. But I think it'd be worth talking more about this explicitly. Why humanoid for this? Like, what do you say to people when they say, why not just a mobile base with an arm on it, like a single arm?
Mm-hmm.
Why do we need it to have legs? Why do we need it to have the head how it is? Like, what do you think is special about the human form factor? And why would this make good business sense?
Yeah. So we often get asked why humanoid, right?
I'm sure.
It's a very common question. And I think a lot of people are coming from the perspective of seeing companies that just arrive on the scene with a robot that looks exactly like a human.
Yeah, you guys have been doing it for a while.
Yeah, well, not only have we been doing it for a while at Agility, the company was, founded back in I think about 10 years ago. The company was founded a little over 10 years ago. Mm-hmm. The design that we started with was not very human looking at all. Our Cassie prototype, if you go back to those days, was essentially just a set of legs, and the legs looked more bird-like than human. And it was designed to basically emulate a certain set of physics. So interestingly, with Agility, we've almost gone out of our way not to start out trying to aim at a human form factor. We've sort of evolved in that direction by trying to solve for the physics problems around interacting with things in human environments and ending up with something that happens to analogously look relatively humanoid with some key differences. You can see that, our legs, for example, don't have the knees bending in the same direction as a human knee. Now, will that change in the future? Maybe, because from our perspective, it's not about whether it looks like a human or not. We might not. It's about the physics of interacting with the world and how we do things like the linkage transmissions to the actuators in our leg. That's what's driving the design. It just so happens that when you're dealing with things that are weights and payloads in human scale and around aisle widths and things like that are, again, sized for humans, you start to find that you're optimizing towards a human form factor. The legs end up being similar in size. In order to move human payloads, you need to be about human weight and human height. A lot of these things just end up converging, even though we start out saying, like, look, make any arm of any length, and then it sort of ends up being kind of a similar length to a human arm to reach these types of payloads. Why two arms? Well, a single arm can contact a payload at a certain point. But the interesting thing about it there is that you have to exert all of your force around that one contact point with your payload. So if your payload's really big, then what's going to happen is oftentimes you're going to grab it at the corner, and then the rest of the payload's going to break off. Like, I don't know if you've ever tried to grab a really heavy cardboard box from just one corner. Not super great. And so you can either make a specialized gripper to try and exert torques and large forces across that, which is what a lot of special purpose systems do that are handling just cardboard boxes. Or you can add a second arm to hold another corner of the box. And now you're exerting really small torques comparatively because you can do it at 2 points on the box. Now, could you do it with 3? You could. In fact, some researchers have taken one of our research digits, the V3 platforms that we produced several years ago, and they've put a third arm on it in a research application. But the more arms you put, the more expense you're adding. And so 2's sort of our minimum. It's the least arms that can handle the range of payload sizes that we think is
you probably hit diminishing returns in terms of value.
Right. And so you end up
the more arms you go.
Yeah, exactly. You can make an octopus robot, but then that's a lot of complexity. You're trying to find the minimum complexity to solve the problem. And so similarly, now we have two arms, because of the way that we're manipulating payloads. So why legs? Why two legs in particular? You end up with a similar sort of thing, right? You want to be able to dynamically balance loads in a really tight form factor. So you want to have the smallest footprint on the ground so you can navigate through these really small aisles, but be able to access a really wide workspace with the robot, really high up, really low, without expanding that footprint. So if you're doing that in a statically stable way, which is what a lot of the robot bases with arms on them are doing, then in order to do that, you have to make sure that all of the dynamic loads with your arms essentially keep you within the stability polygon. So the dynamic loads are like when you're moving a force back and forth, you have some weight and you're moving it back and forth.
Yeah.
Dynamically,
you don't want to get out of your support polygon.
You're moving your center of gravity, you're moving your center of pressure around in the polygon of where you make contact with the ground. And if you go past that, then you start to tip, which is bad news, right? So if you want to do that well with a static base, you have two options, right? You either, as your payload increases, you increase the weight of your base, which moves your center of gravity down and means that you move that center of pressure around less. Or you make your footprint really large, which makes your polygon big. And so you can move around more before you get to the edge of it, right? But both of those are compromises that you have to make in terms of how much your robot weighs and how big it is physically, how wide it is. Now, with a dynamically stable base, you can have a very small footprint and dynamically change where your stability polygon is while you're manipulating stuff. So we can put our feet in very specific positions and push reaction forces through them to be able to maintain this really narrow footprint, even as we're moving through a pretty large workspace. So that's what we've found is a really valuable thing. It means that in a lot of different scenarios, in a lot of different environments, whether it's narrow aisles or in situations in which there might be something on the floor that you're stepping around, like a pallet, having the ability to really control that stability polygon and place where it's being, where you're going to construct it and exert forces all the time to be able to basically control your whole body rather than just react to the disturbances of the upper body, lets us do a lot of motion of payloads with a lot of dynamic load in a really compact footprint. And we think that's something that provides value. We think it's a reason that we're able to go into a lot of spaces where we can get really up close to things and we can access, really large swaths of area. Now, there's still going to be a place for those static robots, and I would expect that we'll see them coming on the market as prices decrease and things like that. But when we're talking about what scales really well and what can move from environment to environment, we're pretty confident that by starting with this base level of functionality, we won't have to adapt a whole lot as we get into more complex environments where there's more occlusions, where there's more narrow spaces or things that we have to fit in and around. Because again, we're human-centric. So we're roughly going to be able to map to the same ground footprint that a human would need to move those same loads around.
Yeah. Okay, another one with this. And that's very interesting, all of that. And that makes a lot of sense. One other question that I hear often is why not have wheels on the feet? So you have legs, and so kind of like the Boston Dynamics, I forget what it's called, but has legs and then it also has wheels at the feet. And then I think Unitree have some of these. Yeah. What do you think of this form factor?
So we have seen it. So Boston Dynamics had the handle platform, which was kind of a balancing robot on two wheels.
Super cool.
Yeah, very cool. And there's I think Hexagon is trying to make a similar platform with two legs. We'll see how that goes. And then the Unitree, they have the Go W, which has the wheels at each foot. So combining wheels with legs, it's an option that you can do. There's a couple of caveats to be aware of. And I won't say that Agility will never explore having wheels at the bottom, but there's some trade-offs that you have to kind of consider. The first is if wheels are part of the dynamic stability, which is the case with Handle or a Segway, or there's been a couple of companies at various points that have made balancing bots on top of balls. Bossa Nova at one point, for example, Bossa Nova Robotics, and there's a couple of others. The challenge there is if you start to lose stability, so say you go over a slippery patch, right, and you lose contact and you start to lean, the way that you have to correct a lean in a robot that's dynamically stable via a rotary joint, like a wheel or a ball, is that you have to accelerate under the robot and essentially catch up the wheel
Inverted
to be
pendulum
underneath where
challenge.
the inverted pendulum is. Exactly. And if you fail to do that, your only option is to accelerate more. And so you end up in this sort of degraded state where the only thing that you can do is to try and speed up the motion of the base. And the more that you're doing that, you're spinning up, obviously, the inertia there. And it's easy to get into a sort of unsafe, dangerous cycle where you're essentially accelerating the robot because you're destabilizing. And so the more you're falling over, the faster you have to go. And that is not a good loop when you're trying to get a safety case worked out.
Yeah, that's very interesting.
And as someone who's face planted a Segway before, I can tell you that the loop gets really fast sometimes.
You were driving it?
Yeah. If you take a Segway sufficiently off-road, you can get this to happen.
To face plant it? I had one where I was riding a Segway and you lean a lot to keep it accelerating and then it like kicks forward or something.
That's it doing
goes
this
into
exact
a faster
thing. Yeah.
Yeah, to stabilize itself and keep its center of mass under its support polygon, I suppose.
Right. And so if you lean really far forward, right, it loses the ability to go fast enough to keep up with that. And that's when it starts to get a little bit hairy.
So wheels basically make it so it's hard to it's harder to think about safety for this because you have to outrun its falling over if that occurs.
That's specifically in the case of when they're a part of the dynamic stability. Now, you have other robot platforms, and a good example of this is the Unitree Go W, where they have the wheels just on every foot of a quadruped. So there you're really just using wheels to create a fixed velocity on your otherwise dynamically stable base, right? They're using the legs to do all the dynamic stability there. And that's a very different thing. That would be the same as if you, for example, made like roller skates on each foot of a biped, because you're still using the feet as feet. It's just that you can also induce a velocity on them. So that doesn't necessarily have the same constraints because it can degrade by breaking all of the wheels together. You're basically just turning it into a foot. But it's a lot of extra joints and a lot of extra power and mass that you're putting at your feet, which ideally the less mass that you can put in your foot, the faster you can move the foot to do the stepping. So in some sense, if you make a really heavy roller skate or like a skateboard that you're riding all the time, now if you do need to move your foot to do, stepping things, you've put that much more mass on it. So it's a bit of a trade-off that you usually don't want to take on until everything else is sort of solved for, right?
Now, so in the environments that you're in, that agility and digit is in, are the floors rough or anything like this? Is it like, I'm wondering about how that trade-off would be, because I get that. So if you have wheels that act as roller skates and you are just kind of using them to move faster, but you can turn them off to have them brakes, so then they're just regular feet. I get that they are heavier to pick up and thus you lose more energy when you step. But would you lose less energy if you were just traversing on a flat floor with them? Or how would you think of that kind of thing?
Yeah, if you're just comparing wheels to legs when you're moving around in a flat environment, wheels will be more efficient. They are for humans as well. That's why we have things like bicycles and so forth ourselves, right?
The hoverboard and whatever else,
It shouldn't necessarily be that much of a difference in short distances and when there's a lot of things like turning and reorienting involved. There, if you're doing an efficient walking gait, and again, you can do an inefficient walking gait, this is something that you have to actually design for. You want low mass in your legs. You want to have a good control algorithm that's not making huge static forces in your toes and things like that. But once you get all of that right, it's not too much worse to be doing walking in these small areas, like turning around in small, work cells and in between aisles and things like that. Over longer distances, a wheel is a little bit better. Now, where it's more interesting is actually not in the, hey, I need to step versus drive and I am using a little bit more power. It's I unexpectedly need to change my stability polygon because I, maybe misstepped or I clipped some object, right? Like maybe I'm walking along or
It's
maybe
tripping.
driving
Yeah.
along, and I encounter the edge of something like an anti-fatigue mat, or someone has left something on the floor, right?
Yeah.
With Digit right now, we'll very quickly be able to do what we
Step
call
forward.
step recovery, right? Where we essentially sense that this is a disturbance and start moving our foot really quickly to a new point, go over or around the obstacle to a new point where we can reestablish our stability polygon. If you create a lot of mass on the end of your foot, it actually changes how
Slows
fast
it
you can
down.
move it, right? You have a lot of inertia to move. So now you need bigger actuators to
Interesting.
do that response and use a lot more
Oh.
power to do that response. And that makes it harder to do. So having fast and
Yeah.
light feet really lets you be very responsive. And that's the bigger thing that you're losing when you put a lot of mass in the feet, is actually that things like step recovery, you're now going to use a lot more power and you're going to be sluggish to respond. In the same
Yeah.
way that if you're a human and you're wearing like really bulky roller skates, it's definitely going to be easier to trip you up than a person who's just going around in, like cross trainers or something.
Yeah, for sure. Makes sense. Yeah, because if I think of a lot of times, like if I trip, I'll like run out of it almost, this kind of thing. And that's because of that fast step that you can do to recover. And that's what the robot needs to do. And if you have super heavy feet, that doesn't work very good. What do you think about the idea of like a humanoid torso on a centaur kind of, or on a quadruped base for this kind of thing? Because it seems like you could have a lot of, you could have a lot of the benefits of legs and even wheels, but then you don't have things like these, the tripping issue as much, because it would be better if you had 4 legs if you were to trip. But I guess it's more parts, and it probably can't turn around as easily in narrow spaces. But how do you think about that kind of thing? Because a lot of people have mentioned that like a centaur shape seems like a very optimal shape.
Yeah, I think you more or less nailed it, with the footprint really being the thing that becomes quite inconvenient. So if you start to build a 4-legged platform with a torso on it, you start to get into the same degradation of, you're starting to really take up a lot of footprint on the ground in order to do that. And that really impedes you being able to get into some of the narrow passages that humans are expected to operate in, and therefore robots like Digit are expected to operate in when you're doing things like going between a conveyor and a shelf down an aisleway or something like that. You wouldn't really be able to turn around a Centaur robot as effectively in those spaces. And it's not too different once you do all of that versus what you might need to do for have a statically stable wheeled base in kind of that same form factor. You're also taking up, similar expansion of the ground footprint. So the Centaur robot is sort of an interesting point in the space. It's maybe not clearly so much better than just doing that with a statically stable base that's that large if you're going to do it anyway. Folks will explore it, but really that isn't necessarily a great trade-off if you're trying to get in up close to different types of machinery and applications. For the same reason that it's not super convenient to take a small horse through an office building, right?
No, but it'd be great to see. That would be funny. Okay, hell yeah. So tell me more about Digit and the applications that you guys are using it for. So it's a lot of tote manipulation and moving objects. The last time I thought Digit's hands were flippers. Like they only had 1 degree of freedom. Maybe they have a wrist actuation too, so 2 degrees of freedom on the hand. But Digit's design is modular, so that you can swap out parts. But tell me about the tasks that Digit's doing, and I guess the end effectors and how it's equipped to do those.
Yeah, so right now, Digit's primary use cases are all material handling. It's where we wanted to enter the market. So Digit right now has FRUs, or field replaceable units, that are essentially the limbs of its body. Its arms and legs are the field replaceable units. So we can swap out an arm, and usually we just swap it out with another arm. It's service operation. But when we want to change functionality of an arm, we can swap out an arm that has a different end effector on it, for example. And so the end effectors that you're talking about, that sort of flipper style of end effector, were actually from an older generation of Digit that was moving around types of cardboard boxes and certain types of very friction-based material handling contact points. So it kind of clamped down the sides of that. What we've switched to and have been using in most of our deployments now is actually what looks like almost like a pincer. So it does have, it has essentially 4 fingers, 2 pairs of fingers and thumbs that grab something like a tote at sort of a front and rear pinch point. And so those work really well for things like bins and totes and other types of containers that have an overhand grasp position. And since we've been doing a lot of that type of material handling, those grippers have been the ones that we pretty much most commonly deploy. And those are the ones that you can see in our deployments to conferences like ProMat this year, where we were showing off our new V4 production units with the expanded battery packs and a new version of that opposable grasping gripper with the 4 fingers. So that's what we've been deploying on those robots primarily. As we're going forward, what we're planning to be designing into the next version of Digit is actually just a tool flange, so Digit can just change out its own end effectors as it sees fit. I mean, that's where the industry has been for industrial manipulators for some time. So it's not really a surprise that it makes sense for us to pursue that.
I know,
and basically
but it's awesome.
Subdivide our field replaceable unit into an arm and a hand, essentially. Although the hand might not be a hand, it might be a claw or a hook or maybe a hand.
Could be anything. Could be a saw, could be a soldering thing, could be anything. Super, super cool. I love the idea of like tool changing robotic parts. What the robot's doing, that's like, I don't need that anymore. It switches its hands, grabs a more optimal hand. It's so cool. We're in the future. It's unbelievable.
Well, it's really funny because a lot of times you see people really thinking about, these 5-fingered hands, and they're trying to jam just like, 20, 30 degrees of freedom
complex.
That exactly replicates what our hands do. But if you really think about it, there's 2 kind of things there. One is, if you actually look at how people grasp things, it's not like they necessarily use all of their degrees of freedom for everything. And you have a number of folks who are highly capable who don't have all of those degrees of freedom for various disabilities, medical conditions, or things like that, right?
Whatever it could be.
But they're highly capable. And even people using various types of prosthetics can be as dexterous as any robot on the market today. And so it's clearly not that you have to exactly be replicating a human form factor to get to dexterity. There's some notion of dexterity, which is helped by having some part of those degrees of freedom, but it's sort of an open question of what's the important bit there. And certainly now that we have AI-based models for training it, we can explore that space in a lot more effective way than we could before by learning about how to grasp things with various types of gripper configurations. And then
you mean making a simple gripper go a longer way through, I don't know, reinforcement learning or something like that, where it goes and iterates and tries everything and you see what you can do with it?
Right. If you look at a lot of the work that's coming out of groups that kind of started with the Aloha work, but now, you see companies like Physical Intelligence and Dyna really showing off that even with simple 2-fingered grippers, they can do a lot. Really complicated folding, manipulation, and things like that. Really, I think there's a lot of low-hanging fruit available in being able to unlock dexterous manipulation with what we can do with relatively simple grippers. Now, I think that the same techniques might also unlock a lot of utility out of really complicated hands, but really complicated multi-DOF hands means a lot of failure points. It means that when you move to high loads,
very expensive. All
of those degrees of freedom are now expensive because they have to dealing with the large forces of a big payload or something like that.
Totally.
So I think there's this notion of dexterity, and we all agree that more dexterity is more capability, but does more degrees of freedom equal more dexterity is maybe an open question, versus maybe you just need a gummy hand pad or like a big clampy thing, that's sort of open, right?
I think a thing that I always think of when I see those like really ornate hands with all the degrees of freedom, it's like, I don't know where I heard it. Some friend or something was like, it just keeps nerd sniping people where they like want to go build the perfect hand replica. And it's like the utility of it's not that good, but it's a very interesting problem for this kind of thing. It's fun to work on. But
it's a beautiful engineering problem, right? But
totally.
Then I go take their hand and try and pick up a 50-pound tote and break all of the fingers off of it, and then it's like, all right, well,
and then it's so expensive and time consuming to repair, and repairs take a while.
So we'll see where that is. But the second piece to it, right, is that there's plenty of things that we do in our own environment where we really could do it a lot more effectively if we had tool changing. Like if I'm using a drill, right, all the entire handle assembly and trigger assembly and speed setting and
Yep.
all of the features of that drill that are just there because a human can't plug into it and have a direct IO connection that says, drill, please turn at this speed with this torque.
It's so freaking cool.
It's just, that's a sort of local problem to us, right? Like a robot doesn't have to have those problems. And so we can just engineer our way around them, right?
Super, super cool. Yeah, it's really interesting because I guess it's cool to me to see robotics going from very specialized towards the application to more general form factors now, like humanoids. And then it's super cool to see the ability for humanoids or whatever form factor to do tool changes to better suit itself to whatever the task is it's doing. Super, super cool.
Yeah, I feel like we're seeing the convergence of all of these different seeds of technology that have been advancing in the background for years. So things like energy storage getting better, things like actuators getting more power dense and more mass efficient. And of course, on the compute side, just more powerful compute and better AI modeling and techniques to be able to control complex systems and interpret complex perception data. All of these things have been sort of raising their water lines and are all crossing over to create this new generation of much more complicated physical systems. And so it's really cool because essentially the water line is just rising, and we know that we can do these things now, and it's just created this new level of capability that I think is really going to change how we approach automating stuff in the future. We just can do this now.
Yeah. I think the thing that's interesting to me is it's like before it felt like, oh, that's not feasible, this won't work. Now it's like, it's not efficient kind of thing, which is an interesting shifting. For everything.
It's really funny because having gone through that, Agility sort of went through that path where when Agility first started, you were convincing people that a humanoid could even work. And you'd be like, come to our facility. Like, look, we'll show you one that works. And now it's a lot of people complaining that they work fine. They totally believe that. They're like, come into our facility. We 100% believe you can solve this problem. And of course, they'll give us some incredibly complicated, very difficult problem. And then they're like, why aren't you doing it faster? Like, go faster, be cheaper. And you're sort of like, guys, like, 8 years ago, you wouldn't have even believed that you could do this. And now you're complaining that it's not good enough and you should be doing it better. You know?
Yeah, it's an interesting thing. Let's see. So, well, tell me, you alluded to it a little bit. So you have your version 4 robot. And so that's the one that you're doing now. And that's that one that has that interesting gripper that you mentioned. And you mentioned that you have a version 5 coming. To me before, and you mentioned it a little bit. Tell me a bit about that and tell me what's changing.
Yeah, so with the version 5, the big change is version 4 is designed to work out in industry and be compliant with regulatory standards for working in a facility with an external safety system, with some form of a work cell around it. So we need to separate the robot from humans. Now, the robot has an onboard safety system, but it doesn't necessarily have all of the onboard capabilities to detect humans and to be able to dynamically change what it's doing in response to humans getting close to it. So we need to either put up walls around it or somehow segment where the robot works from where humans are. And if a human enters the space, we basically kind of shut down the robot before we let the human enter the space. Our big design change with our V5 platform, which we're working on right now to come out in about 18 months or less, is to be able to integrate all of that safety on board the robot and make that robot safe and compliant to operate cooperatively around humans, which is to say that the robot and humans can move through the same spaces together without specific guarding or protection around them. All of that's included on board the robot. So they can't necessarily work on the same thing at the same time, that type of collaborative safety, because that requires a little bit more than what exists right now in the safety industry. It requires some fairly advanced technology there that doesn't quite exist. But pushing what we can do now to its boundaries, we can do cooperative safety, which is that the robot can detect humans in its vicinity and limit its motion with respect to that using onboard safety systems. And so that's really pushing us to do this reinvention of the digit technology stack to incorporate safety at every level, from the physics of the robot itself all the way through the drive systems, the drive electronics, and the low and high level software to build this new platform. So it's pretty exciting. And we've been doing a lot of work, not just from the robot design perspective, where we've been developing out a lot of new technology for AI-based safety and onboard dynamic stability, but also on the safety side itself, where we're also developing out new standards that can use these types of models as part of a safety strategy that we can take to a nationally recognized testing laboratory to basically guarantee and certify that our robots are in compliance with industry standards. So that's been a huge effort as well, and we're pretty excited about that. And we just recently basically created a new ISO standard that's in development. So we're now working on a specific ISO standard towards safety for industrial robots that use dynamic stability, which is robots like Digit, where the dynamic stability has to be part of the safety strategy.
Okay, tell me about that.
So in previous standards, things like ANSI R1508, which deals with autonomous mobile robots, a lot of those standards basically have gaps in them when it comes to how they're applied to a robot that's dynamically balancing. They kind of make the assumption that you more or less probably have a statically stable robot. It's either bolted to something or it's on wheels or something like that.
Because that was true in the past.
Right. It was true for industrial arms. It was true for most collaborative arms and for AMRs, autonomous mobile robots, which are primarily wheeled bases that have, shelves and things mounted on them. So that means that a lot of the standards essentially say, oh, well, in order to guarantee safety, like here's how you're going to depower the entire robot in this type of scenario.
Safely.
Right.
Yes.
Which works if locking up your wheels is a thing that makes you more safe. It doesn't work if turning off all of your motors is a thing that makes you so that you can no longer keep yourself upright, which is the case in any dynamically stable robot. So it's the case in Digit, certainly with legs, but it would have been the case, for example, in the Boston Dynamics handle robot, or if you were trying to make a Segway that could work with an industrial arm on it or something like that. That's also a dynamically stable robot and would have some of the similar gaps in specification in the safety standards. So this new effort, which we're doing in collaboration with other folks, Boston Dynamics is also participating with our team.
Cool.
It's a collaborative effort with a bunch of different providers that are working on these types of platforms to basically define out how do we do this dynamically stable safety? What do we need to specify? What do we need to describe so that we can ensure that a dynamically stable robot that's doing certain things at certain levels of reliability could be considered safe enough to operate in an industrial environment? And it really is kind of like clarifying some of those details to get this to match with broader, industrial standards for safety of machinery as a whole. So all of these standards are kind of building up. So there's different levels of standards like type A through type C. And the idea is that you have broader standards that essentially say like, make this robot safe. And then more specific ones, which are around, and here's how you make a wheeled robot safe. And here's how you make a collaborative robot arm safe. And now here's how you make a dynamically stable robot safe.
So how do you make a dynamically stable robot safe?
Yeah, it comes down to a few things, and there's a little bit of secret sauce in there that we're building out. So I can't talk about all of the detail, but what we think is kind of primarily important is that you need to understand where people are in your environment, and then you need to be able to be maintaining essentially a safe operating envelope for your own robot that you can guarantee in the events of faults or failures that's within the space of where people are. So you have to essentially say, how do I keep my robot such that it's bounded in how it's going to move or exert forces or even trip and fall and things like that. So it'll always end up within this bounding radius or this bounding sphere or whatever it is. And I can make sure that
there's no person.
That people, as they're approaching, I can shrink my radius down by doing things like slowing down my motion or getting closer to the ground. And so it's this whole dynamic process of how do I enforce that as a person gets closer to the robot is reducing its hazard by the things that it can control about its balancing and its posture.
Mm-hmm. That sounds really cool. So I'm imagining that a robot is moving through a space and it's estimating where there is risk for it falling and doing damage. And what it's doing is it's making sure people aren't in that zone for this kind of thing. And there's probably some risk negotiation there where, oh, it's a tight space and I have to, so I'll go real slow or something like that. It's similar to that kind of thing?
Yeah, it's this idea of basically trying to figure out where your various levels of hazard can be, and then what can you do to, you can either go faster and increase that radius, or you can, do things like go slower or use lower forces and shrink that radius. And now with that lever, right, if I can combine that with detecting where people are, and I think detecting where people are is kind of an important piece here, because you're on a platform whose job, right, the thing that you're getting paid for to do is exert large forces on objects, right? I need to pick up a 50-pound tote. That's a huge force. That same force, if I apply it
Does Digit pick up a 50-pound tote?
So the newer versions of Digit can pick up to...
That's heavy.
Yeah, that's 23, 25 kilograms. That's what we're targeting for our V5 platform. The existing robot can, within its entire workspace, do 16 kilograms, and it's higher as you get a little bit closer to the robot.
So 30 pounds?
Yeah, like 33 pounds roughly.
35.
Yeah, and it's doing that. It's doing that, all day, every day at facilities, actually handling those loads.
It's awesome.
So, yeah,
50 pounds is awesome.
We have Digit, doing little dumbbell curls with sandbags and things like that.
Yeah, with a barbell and whatever. Hilarious. I would love to see those videos. That's great.
Yeah.
Okay.
So basically, once you're doing that, right, you can't limit yourself just by saying, oh, I'm really close to something that could be a person or a shelf or something. I need to turn down all of my forces. Right?
Yeah, it'd be useless.
And you'd never be able to
carry anything.
Exactly.
For sure.
So that's why understanding where people are is such a big part of having a functional robot that can also be safe.
Mm-hmm. So that sounds like a lot of perception is required. I'm imagining almost like I'm thinking of Tesla and their cars and how they see everything around. And so I'm imagining that you need something similar so the robot has no blind spots, so that you can go and look at everything and assess where things are. Or you need a good map of the environment, but then always a person could sneak up behind you if, say, you only have forward-facing eyes, and that would make your estimate bad. So do you basically have like super aware perception? Like, is that part of the standard, or tell me about the perception side of this?
Yeah. So there's two pieces here to making a safe robot. The first is the standard, where we're essentially writing the rules. So in that part of things, we're not really defining like, should you use cameras or should you use LiDAR or things like that. You're really defining like, what would you need to prove in order, and what would you need to verify?
The standard is modular in a sense because of that. You're making there's no assumption on how you get this data about the environment. You just said once you have it, this is the case for safety.
Yeah, it's defining how do you go about guaranteeing that a dynamically stable robot is safe. Like what are the rules? What are the checks that you need to kind of meet, right? But not the technology. And then on the other side, at Agility, we're obviously developing our platform here to try and be able to meet those rules, right? And that's where we're deciding things like, okay, how many cameras or other types of sensors might we need? Where would we place them? You can, for example, choose to have fewer sensors, but then need to maintain more state about your environment. So essentially you could say, well, as long as I remember that I passed by this area and a person wasn't there, I could assume that someone couldn't have snuck in because I can see around all of the places that they could come in from, even if I can't see that specific spot, right? So there's some amount of that, but then you then, if you lose that line of sight or you get that...
or they were hiding in a shelf or something.
Yeah, so then there's edge cases you have to deal with where you have to maintain that state, and that might be better served by just adding an additional sensor there or some other type of routine that clears the space for you. But you have to make those trade-offs, right? And so we do plan on having a bunch of sensors. That's, I think, an important part of this. But there is also some amount of understanding exactly how the environment evolves from a safety perspective and clearing certain areas or reasoning about where could a person be realistically, given that this is what I've been doing. Like if I was just in that space and I could see all of the areas around it that a person could have moved from. So a person couldn't have, teleported in there, right? They would have to have already been in there, in which case I would have seen them before or after, something like that, right? You can have that type of reasoning. Now,
yeah, for sure.
It'll be a combination of some amount of understanding that from the safety side, right? And also just having really good sensing and a variety of sensing that can reliably detect humans under a variety of circumstances.
Yeah. And one thing that's really interesting to me with this, from how you described it, I think you said it like on agent or onboard safety for this kind of thing, as opposed to we have cameras everywhere and that gives the robot the perfect it gives the world perfect observability for the robot. And maybe that would work, but it's less flexible in its ability to deploy because you need power and data, ability to stream data if you have cameras everywhere. And
so you can actually pair even the V4 version of Digit, right? So the V4 version of Digit's designed for an external safety system. You can pair it, if you have one, with a safety system that's using external cameras or external laser in various forms, whether it's 3D, LiDAR, or things like that. And people do make systems for doing external safety where they are detecting people from a third party, not a third party, but from an external perspective. You put cameras all through your facility or some area, right? And then you essentially detect where people are and where robots are. And you can use that to then write a rule that says, hey, if something's getting close to a V4 robot, shut it down, right? So you can do that now. It's just that those systems require you to build out that infrastructure, which a lot of our customers are coming to us because they don't want to have that infrastructure in any specific place, because they want Digit to kind of come into an area and be ready to go and maybe move it to someplace else later. And they don't want to necessarily put a camera system here and a camera system there.
Yeah. And you say you have a 30,000 square foot warehouse or something, or 300, like some massive, 1,000,000 square foot warehouse. It's like that's going to be pretty costly to put cameras everywhere.
Yeah, you might be able to do it in a certain work cell area. So that for that use case, it might make sense. And when you can do it, if you can afford the cost, because those systems are not cheap, you can certainly do it, and it might be even better than having onboard safety. But it's really about, again, the infrastructure versus the flexibility.
Yes, definitely. Yeah, and you guys are heavily betting on the flexibility, which I think is a good bet in all of this.
It's a part of this space. There's always going to be some part of these industries that needs that flexibility, whether it's a type of industry where the amount of flow changes really seasonally. One of the reasons that GXO is so interested in us is, as a third-party logistics provider, they get new customers all the time. And so a single facility might be changing what fulfillment it's doing, or might add or remove a customer throughout the course of a year. And so you really don't want to be in a situation where you paid for a whole bunch of automation that's at a single rate or a single size, and now I add a customer and it's now the wrong size, and I have to rip it up or add a really big expansion or something. So that flexibility for them is really valuable. And there's other cases in which you have the use of that flexibility is because you might have a really big facility where you're using different parts of it at different times, right? You might do something in the morning and something else in the afternoon. Or there's things like crew shifts where a single person rotates between different stations. So that's really common in certain types of manufacturing. So we have another customer, Scheffler, who does automotive parts, where that's a really big part of where we can bring value to them, is that they have, parts, machining equipment. So things like washers and dryers and heaters and things like that, heat treatment systems that basically batch up work. So you load them up and then you leave, right? And they go, clean parts for 90 minutes or something. And you don't need to be there for those 90 minutes. And it'd be a waste of time for your robot arm to be sitting there for 90 minutes. But after 90 minutes, then a bunch of bins come out and you need to take them and load them into the next thing, right? And so they have people that often do these functions right now. So Digit's really a very useful platform for being able to go between these different stations that need that type of service, but not be there all the time.
Yeah, where you can go have them do something else.
Right, or man multiple stations or something like that.
Yeah. So one thing that I'm thinking so it is a new ISO standard, a new International Standards Organization standard. Why make a standard? So the way I'm thinking, which I'm happy you guys are making a standard because I think it'll improve everything for everyone. But why, like, I'm imagining it could be a competitive advantage. I don't know what the other humanoid companies are doing or dynamic robot companies. Um, but, and maybe having a third party validate things. Can you tell me some of the strategic thinking behind it? Because I'm wondering if you didn't make a standard and just had an internal secret sauce for these safety things, maybe it would be a significant competitive advantage. But how do you think about this?
Yeah. So the standard, I mean, to be clear, right, we still need the secret sauce about how us and anyone else that's trying to do it is going to achieve the standard. The standard itself is laying out the rules, right? The rules for what you need to do. So
they're probably well thought out, and that saves a lot of early work and back and forth with customers and things like this, which I'm sure you did in creating the standard.
Right. But one of the reasons that we're pursuing it is because in order to deploy robots outside of a work cell, we already need to meet standards. Right. So within the US, OSHA, while it doesn't specifically name a certain standard, is basically putting out the expectation that any automation deployed within the US is going to meet a set of prevailing standards. And so you already have ISO standards for things like the safety of machinery, the placement of e-stops, and you're already required to be in compliance with them. They just don't have good specifications for what it takes for our robot to be in compliance with them outside of a work cell. So it's really that in order to be in production in the US and especially in Europe, where it's a lot more important, it's basically a requirement for you to be able to certify your robot at least as partially completed machinery to go into a production environment. Well, you really need to have the document that specifies what you need to do to meet that, right? Because otherwise you don't really have a path forward to say, hey, I'm meeting this requirement. I'm complying with industry standards for best practices here, because there aren't really completely defined industry standards. So for us, it's really important that we get these standards out there and written and specified, so that with our customers together, we can go out and ensure that we're in compliance to meet the legal obligations that we have when operating in the US or abroad.
How do you think it works with other humanoid companies?
Well,
say like Figure with their, I think, BMW partnership, or Tesla with their Tesla or 1X, or
So right now, the way that pretty much all humanoids can be deployed is kind of in two ways. One is within the US, you can deploy them, not directly into production applications. You can deploy them into basically research environments or other types of innovation spaces. And those don't have the same standards requirements. Obviously, you still want to make the robot safe, but you're not being specifically directed to like an ISO standard for an industrial standard if you're deploying it in essentially like a research lab or an innovation part of a facility. And so in a lot of cases, and certainly even in our earlier POCs, we'd often be deployed into an innovation center or into a special facility that has some portion of the facility essentially running non-production workflows. And the difference there is that when you're deploying in a research environment, the requirements are a little bit different because your exposure is a little bit different in terms of the people that you expect to be around the robot and how the robot's being operated. When we're talking about why it's so important to meet industrial safety standards, part of it is because once a robot's deployed in a facility working full shift work, the types of people that are around it and their level of training with respect to the robot is different. And the amount of attention that they're paying to the robot is different. These are people who are now, they're not there just to work with the robot. It's not like an innovation center where the whole point is to look at the robot and see how it's doing. They're trying to do their own work, right? Their job is not to follow the robot around. It might be to walk past the robot and do something else, right? And so they're not necessarily paying the same level of attention, certainly over 8 or 16 hours. And so
for sure,
that's why it's so much more important that you're ensuring that the robot performed to a certain level of reliability and how it's doing the safety. So there's this one aspect, which is that, you can deploy into different environments that are not the industrial production environments. And a lot of people start out there. The second piece is that you can deploy humanoid robots, and we're doing this right now, in conjunction with a work cell. If you have another system that's around the robot, that's really what's keeping humans safe, and maybe that is plexiglass panels or a light curtain or something like
that bounds it.
Then you can do that, right? You can put that around the robot and then achieve some compliance with safety standards, at least in North America right now. And that's why you see that that's what a lot of people are doing. They'll deploy into parts of facilities, or they'll deploy in use cases where the robot's really not moving between stations, or it's moving around within some restricted zone. And that's how we operate right now. At GXO, we have a restricted area that the robot operates within, and it has a link to an external safety system that helps guarantee that we can shut down the robot from outside of that work cell if we need to go into it.
Cool. Do you know if any of the other companies making humanoids have their robots in production? And if they do, they're probably in work cells, I would assume. But what do you think is the current state of humanoid robot companies other than Agility?
I think that it basically, because of the way that the standards are defined, everybody has to at best be in production in a work cell, or if they're not in a work cell, be in a non-production environment in general. That's just, everybody has to follow the same rules there, at least within North America and Europe, right? I think we often see one-off demonstrations of technology, and certainly we can do them too, right? Like we did a recent demo for Google where we worked together using their new Gemini models to go pick items off a grocery shelf, right? And that was in our innovation space, and the robot, grabbed a little basket, and I think we told it to get the ingredients for spaghetti or something, and so it's picking tomato sauce and pasta off a shelf, right? The robot could do that, right? But it can't do that in production, right? That's not a production capability, and that's in part because that's not something that it could do without a work cell around it, right? And that's the same for us as everybody else. Anyone who's doing this legally has to be following the same sort of practices.
Makes sense. So you needed to do this to enable a lot of high potential things for you guys to do. You had to create this standard because there was a gap in the existing standards because these robots are so new. And with this kind of thing, with this additional standard, once you write the standard, then prove that you meet it, then you are able to have your robots expanded to a much wider number of applications, probably, or much larger applications where you are working outside of a work cell for all of this.
Yeah, and that's exactly why we went after it right now, because what we're really seeing is that as we're moving into the space, there's a lot of capability that we can show, that others are showing, of the platforms. We could pick groceries off of a shelf. We can walk around outside. Digit can walk around outside.
Oh yeah, totally.
We don't have the safety rules about how one does that for a lot of these environments. So we're really seeing that safety is a key gating item for getting dynamically stable robots out into the world. It's actually probably going to be lagging behind these capabilities to do things in this space. So we'll be able to pick groceries off a shelf. We can pick groceries off a shelf, but we have to come back with, well, what are the safety cases for doing that in a retail environment? What are the safety cases for doing that in a construction environment, in a home eventually, right? Those have to be worked out. And homes are particularly challenging. They're sort of the hardest case, because not only do you have all of the lack of structure of, I don't know about your home, but mine's not the neatest, right?
Chaos.
Right, exactly. But, to exactly your point you were mentioning earlier, you've got a small child and you've got an animal in your house. And in both of those, as small children and animals, pets, right, are things that you have to be safe around if you are a robot. And you can't expect them to either be trained or avoid a hazard, right? You can't be like, no, we trained all of the puppies to never come close to the robot. Like you can't, no, I have to make my robot never do anything that could cause a hazard to your puppy, right? That's the way that works, right? And that's a pretty high bar. That's way harder than in an industrial facility where
Very
It's
much.
pretty much adults. They're probably receiving some sort of training. There might be PPE restrictions on certain areas anyway, and those are reasonable, what's called administrative controls that you can put in.
Yep.
Your robot still has to have a certain level of safety, but you can do that in conjunction with some of these administrative controls. And that really simplifies things quite a bit, right? In a home, like you
It's chaos.
have to be taking care of it. Everything has to be on your side. You can't induce a hazard that could harm any of these individuals, an adult, a child, a pet, and you have to assume that they are not necessarily doing anything to make your life easier.
Yeah, very much. We also have chickens, and those would be chaos near the robot. And it's funny because they go to you when you go outside, so they would go right to the robot probably.
Yeah, exactly. Just running around its feet,
Yeah. Hilarious. Okay, that's a very interesting thing. So do you think that, how do you imagine these safety standards? So is this ISO standard, are you working on it, or is it done, or?
So we just got
what's
approved.
the status of it?
Yeah, we just got approved to create the working group for it. So now there is a working group, a team, an international team of ourselves and other robot companies and other industrial automation companies that are participating to define it and build it and ratify it. So that's where we are right now. Is we've got the group together. We've got approval to go after this. Everyone's recognized that this is an area that needs a new standard, and so now we're building it out together with other folks in the industry.
What does the timeline look like for this? I guess the whole thing would be interesting too. Getting the working, I guess that's logistics, and you just have to be approved. What's the timeline look like for this?
Yeah, so it does take a while. We do have the benefit of one of the key folks on our team is Melanie Wise, who largely did this work before for the R1508 standard, which is the one that is used for AMRs. So luckily, having her is hugely valuable because she's been through this before with a different type of robot. And so she's been working really hard with the other folks on our safety team, like Kevin Reese, who's also phenomenally knowledgeable about this space, to basically build out the standard and sort of get all the pieces in place. But that is definitely accelerating the process because it can take a number of years for a safety standard to really go through all of its paces. But luckily, with some experienced folks on the team,
it will be a bit easier.
It should be easier, and we really hope to be able to get our V5s out in the world and get them CE marked within the next couple of years.
CE is like, what is CE?
So CE, that's a marking that is used in the European side of things to basically mark that you have approval under certain sets of standards.
So for the standard, so you'll make the robots will be capable of fulfilling the standard. The standard will be ratified at some point. Do you have like an optimistic and pessimistic estimate for the standard?
I think it's probably, I think I don't necessarily know exactly. Melanie is the person who has a much better intuition of it. But I mean, we're really talking, single digit year, couple of years, few years at most. We're really expecting
so like less than 5, hopefully.
Yes,
maybe
definitely.
3 or something
I mean,
that.
I'd say 1 to 3
2
is what I would hope, right? Like it might be quite quick to get to an initial version of the standard, and then we might see where it goes from there, or maybe it takes a little bit longer, but we'll have enough of it sort of worked out that we'll have maybe a working draft or something that we can start getting in compliance with. But that's really more of her specialty than mine.
Yeah. Okay. Yeah, I've had Melanie on the podcast a few times. Melanie's awesome. Hearing her perspective on that would be very interesting. But super cool. I really like that you guys are working on the standard. So with your knowledge of standards, I know that she's kind of like, she's been leading, right? Like she has the experience with the AMR one, but for robots to enter the home, or say like a grocery store or places where there are more people that are less trained, how do you imagine that will occur? Do you imagine that we're going to wait on standards like this? Or will it be that companies just kind of go with it and suffer the legal consequences when they like step on a kid or something? Or how do you think this space, like how do you imagine the space moving forward?
Yeah, that's a good question. I think that we should be building out standards as we go. I do think that once we have one good reference point, that does make it a lot easier to move to the next one and the next one, because we can largely build off of that or reference it, right? Yeah, you can leverage it. I would hope that we're not going down the route of people just winging it and trying to get insured anyway, and then having something horrible show up in the news about a robot stepping on someone's toes or something. I don't want us to go.
I mean,
down
that already happened in some places, but
it's definitely happened at some conferences and trade shows where they've been showing off smaller humanoids doing stuff. Because those humanoids largely run without too much safety system oversight at all.
For sure.
But I don't want that to happen. I mean, I think it could be a big black mark on the industry if that's how we approach the problem. I'd really like to see us get there in a safe way and with a pretty good understanding of what we're doing. Now, I think there's two pieces that might accelerate that. One is that obviously with an example reference of like, here's how we're doing it in industry X, going to industry Y gets a lot simpler, like we said before. And then I think the other thing is if we really show a lot of capability, then there's a lot of industry pressure to figure out the standards, and it sort of like naturally accelerates the development and the working groups and really the whole process. Like if a lot of people want a thing, right, then it tends to move faster. And so I think we will see that hopefully that the capabilities that we're able to demonstrate in some sense builds a lot of goodwill and interest in building out safety frameworks that can support doing it. And maybe there'll be interim stuff that comes out of it, similar to how drones initially had some experimental airworthiness certificates and things like that let people try out things under special qualifications, or that, we'll see changes in the regulatory space to kind of like provide ways to phase in the technology in earlier stages, right? In controlled settings and things like that. We might see some of that. And we might also just see that, hey, because it's such a high demand that the standards for things like retail industry just move really quickly because there's so much interest in it that a lot of people will spend a lot of energy working on it. Yeah, moving it.
Interesting. How do you feel like you feel like there's significant energy and desire for robots to be out there by these different industries? I know you guys are most focused on material handling, but do you have a feeling for these other industries? Like, is there a lot of pull from other places?
I think there's a lot of interest, yes. I mean, we certainly see a lot of interest. We have folks coming to us all the time asking, can you use Digit over here? Can you use it in my facility?
That's
can you
a
use
cool
it
spot.
in my store? Yeah, it's great. It's great to be there, but unfortunately right now we have to turn down a lot of those folks, which is unfortunate. And we're making a big list of folks that we'd like to come back to, in a year or two, where we could say, hey, yeah, actually now we can go look at that for you. And I think that's part of it. There's no shortage of interest in the platform. It can do a lot, and it can do a lot very easily, in the quote sense, not obviously there's work to get a robot deployed, but like it's not the same level of work as deploying another type of automation where you might really have to design what you're doing around it. You can kind of slot Digit into the process that you have.
Interesting. What do you think? So kind of a tangent, but it seems like in a lot of my interviews, it eventually ends up that companies are planning on doing this kind of thing. So if it sounds like you guys are having a ton of demand for things that you can't service yourself, any interest in like a robot app store or any sort of things where it's like you let developers make applications for your platform to solve some of the problems that customers might have. How would you think around that kind of thing?
So we are definitely going to be moving in that, or we're already basically moving in that direction. So one of the things we launched last year was Arc, which is our cloud management platform for the robots. And within Arc, you can basically build out what we call workflows, which is essentially telling the robot how to do different types of work by graphically putting together building blocks. And those building blocks are essentially skills. They might be like pick up a tote or look for something in the environment or move to a location. But they're basically drag and drop high level skills. And sometimes they're powered by AI models that are trained on things. Sometimes they're their own sort of specialized motions like docking sequences or things like that. But we're designing that platform with the intent of being able to hand it off to integrators and customers in the future and let them edit the workflows that Digit does on their own. They're very high level. They're at the level that you might write a work instruction for a person doing the same task, which is like, go to this work cell and, look for a tote over here, read the barcode on it, figure out which of these 3 places it goes and move it over there, right? You can drag and drop that flow together. Or
Super
maybe in the
cool.
future, you'll be able to use agentic AI and just type that request in and it'll
What you want it to
drag
do.
the blocks together for you, right?
Super cool.
But that's 100% our intent. We don't want Agility employees to have to touch every deployed robot. We want to be able to ship you a kit that, an installer can put in for you, and that you can configure on your own. That's our goal, right? And so, we actually used to have, this internal tagline, like we're going to create the app store for labor. But then now with AI, it's like, well, you don't really have to write the apps anymore. So now we're just a store for labor, maybe. But that's the intent, right? We want you to be able to, we want to democratize the automation of labor activities, right? We don't want people to have to do
Super
this
cool.
work, and we don't want people to have to spend time working on the automation either, right? We want you to just get a piece of equipment, get a kit that you can set up that just does these things for you.
Yeah. One of the things I've been thinking that I would imagine robotics will arrive at some point will be that you can have developers that are building robots or using robots for applications, but they're not building them themselves, kind of like what you're describing. But one of the things that I imagine is in specific domains, you're going to find that Digit needs to interact with something, or there's something that's really hard perception-wise that you guys haven't solved because it's not a thing that you run into frequently, or some thorny algorithm or something. Are you adding developer support so you can have like a module that has custom code written in it, or how does all that work?
Yeah, so that's something that we've been playing around. It's something that internally,
because that's hard to do.
Yeah, well, it's I mean, I'm sure you're very familiar with all of the various attempts at like low code, no code robot environments, right? There's always the thorny edge cases of like, here's a thing that isn't one of the building blocks that you offer, but I need it, right? There's 2 things that are kind of interesting about it from our perspective. The first is that we certainly can do the route of, hey, we'll give you a little sandbox block that is something that you write your own low-level API calls into at some point, right? Right now, it's not super easy for people to do that because Digit's control system and so forth are relatively complex. But this is where the second piece comes in, which is now that we're leveraging AI models a lot more for Digit's low-level skills and controls, that's actually changing the game of how you specify things in this category of new skills in particular. Now, a lot of what we're starting to explore are things like physically demonstrating how to do a task to Digit and then that turning into a block, right? And that's where it's actually quite different from anything we've ever seen in the past where, hey, if you don't have a block you like, you might not author it by using code anymore, right? Which is really interesting.
What a trip. Yeah. Just a learning from demonstration based approach, but it's hard to make them general, but there's a lot of good work going on in that space, I think.
Yeah. And then there's also the question of exactly how general you need to make it, because it can still be a building block in a workflow, right? So
yeah, if you take a bunch of actions that already exist and just compose them with AI that watched it, say.
Yeah, or you just use AI for one piece of the actions. Like, I don't need to use AI to like figure out a new way to move from point A to point B. Like, that's already a skill I have, but maybe I'll use it for, stacking a new type of tote or interacting with a new piece of machinery. I haven't seen that before, but I can demonstrate that and make a new skill. So that's all stuff that we're exploring very aggressively. It's not in production, right? But it is stuff that we're exploring very aggressively internally and working with folks like NVIDIA and Google using their latest models on seeing how we can do on this type of new pipeline for creating new skills. And if generalist models do start to work, well, we're selling a robot solution, right? So we're perfectly happy to be leveraging.
You're very well positioned.
Right. We can leverage any generalist models that come out, because as long as they help us do something, we're able to use it as part of our skill set. But at the end of the day, someone has to ship you a robot in a box and have a way for you to get that up and running and connected to your warehouse management system or whatever orchestration platform you've got. And we're doing all of that. We're the person that you can call on the phone that'll ship you a new arm when yours breaks, or whatever you might need, right?
Yeah. It's a good moat to have the physical hardware for this kind of thing. Because there's one AI generalist solution and then another one comes up and it's like they don't have any moat. You just switch from one to the next. But if you are actually making the hardware, that's a much stronger position to be in. And any AI general solution that comes along is like, oh, great, throw it on our thing. It's real easy. That's great. So hell yeah. How are you viewing all this AI activity? And I guess breaking it down into different areas, and then how do you think about it? Melanie, when I talked to her, it was one of the early podcasts when I started this podcast, was thinking of it kind of like really good search. How are you thinking of, and that's specific for the language models and this kind of thing. And I know that transformers are really interesting and they give you a lot of like interesting abilities across, say, vision or all sorts of other domains. But how are you thinking of it?
Yeah, so we've definitely been growing and evolving our AI strategy internally, and we use now a lot more AI inside of the robot than we did even when you last talked to Melanie, because the field is just moving so rapidly, and we're benefiting from that greatly. I think there's a couple of different layers to it. At least that's how we think about it, is there's a couple of different layers to the AI models that we employ. And that comes not from necessarily what the models can do, but in terms of the places that you use them and what types of requirements there are around how you use them. So at the very lowest levels of the robot, there's the local idea of what am I doing with my arms and legs, right? Like, what do I need to do to not fall over? And what do I need to do to interact with the environment, to exert forces on that? And that's a controller that needs to be very close to the robot and work at a very high rate, because that's the rate at which disturbances to that model happen, right? So that might be hundreds of hertz, right? That's running right on the robot at hundreds of hertz, right inside of our control loops, right?
Yeah,
a layer
hundreds of times a second.
Right, and so that is taking as input, some idea of what am I trying to do with my environment? And then it's going to figure out, what do I do with my arms and legs? So the layer above that, that's like a controls AI model. Then a layer above that is like a skills AI model, which is really thinking
about...
What
are you doing at that lowest level? What kind of AI thing are you doing? Like a lot of, like I talked to Jonathan Hurst at some point, and a lot of it was like really good application of existing control theory, if I remember correctly. But maybe that's not true any longer for these kinds of low-level command or low-level control loops.
Yeah. So what we're seeing,
are you using AI there? And what kind of things are you doing?
So we are using AI there, and we do have a good model-based controller. So like if you see the robot working in production, it's right now flipping between the two. It actually has a really good model predictive controller.
Cool.
But then if things get out of scope of that controller, it actually switches to a reinforcement learned controller that's more robust, that handles
one that you just perturb a lot in simulation.
Well, one that's been trained
likely.
It's been trained against a huge variety of disturbances, and so it'll actually switch to that. But what we're seeing over time is that RL model is covering more and more of what the model-based controller was originally tasked with. And so we think that that's so cool, likely to sort of subsume a lot of that functionality in the future. Now that RL model it's a relatively small model, but it's one that's trained across just a huge variety of different environmental conditions, especially around things like ground contact forces and slip and so forth. And it also takes advantage of still knowing a lot about the robot. So we do have the advantage of, because we build the robot, we can actually co-design the robot and the RL together. Like sometimes we can actually make design decisions to say, hey, we're going to change this actuation in our next version of the robot because we want to make it so that it's easier to model in reinforcement learning. Or hey, like we can go get the actuator parameters or change the control layer
that
here.
coupling is so cool.
Yeah, it is very cool.
Magic.
And it leads to very good
I bet.
sim to real type transfer. So we can do what's called zero shot transfer, which is we can train a controller in simulation
And run it the first time.
and then run it the first time on the robot. Yeah, exactly.
On the robot.
And so that's
super cool.
That loop of being able to just say, yeah, robot RL, is really powerful. And we think is one of the things that, we're really excited about doing well here at Agility. So
hell yeah.
So that all is that first layer, right?
And I have another question there too. And that's so cool. So I was in a legged locomotion lab at the University of Michigan for a while, and we did some reinforcement learning around gaits for a bipedal robot. And it was very hard to use reinforcement learning to converge on stable gaits that we could transfer to the robot. So we'd learn it in simulation. We could get it doing really cool stuff. And then it was very hard to take that set of parameters that we gained and transfer that to the robot to actually make it work like it did in simulation. Why have we seen, and then when there was this sim to real gap that we talked about a lot in robotics. How have we advanced so far, so fast that we can do really good training and simulation and transfer it to the robot for zero shot learning and this kind of thing? Is it just we know to vary absolutely everything about the model and the contact forces and things like that, and that creates a robust policy? Or what have we done to make such a significant advancement?
Yeah, so I think it's been basically
recently
two factors. One has been that there have been improvements in
and more compute.
Well, that's
probably the other one.
Definitely part of it. So one of them is that we have made some advancements in the techniques. Like we're still using like PPO optimization. Like that part has actually stayed relatively constant for these types of low level controllers. But there are some new techniques.
What does that stand for? PPO, proximal policy optimization.
Yeah.
I'm surprised I have that in my head
there
still.
There you go. I mean, it's you probably know it better than I do if I actually doing an RL lab, right? But the key thing there is that like that core fundamental piece actually does work pretty well still with other techniques like teacher-student systems and basically other things that we've learned about how to build a curriculum over time to learn about stuff like locomotion, because a lot of people have been exploring it in this intervening period and found what works and what doesn't. So that's definitely helped. And I think that, a rich academic history there has really helped us figure out these are the techniques that work really well for doing dynamically stable legged locomotion. And we've been learning that this whole time. On the other side, which is really where just the benefit of everybody pouring so much energy into AI has been, the compute that we have available and GPU accelerated simulation is really a game changer, because now you can also just say, well, let's also just run it like 100, 1,000 more trials than we ever could before in like 1/10 the time, right? You can simulate really fast. You can simulate on really powerful hardware. And that means, to your earlier point, when you're talking about how do I make sure that I've captured the parameter space of the real robot, you can just domain randomize over that space and make sure you've captured it somewhere in that cluster of parameters that you're covering, right? And so domain randomization in conjunction with really powerful compute helps solve for some of this. And there is some amount of just, hey, if you train it for longer, you can get better results. And now training it for longer doesn't take as long. And so that's really kind of all come together to make it such that it really is highly effective to build out legged locomotion in a reinforcement learning environment now, and just have an RL system basically train up from whole cloth, how to move in an environment. And of course, you can always add in additional stuff on top of that. Like you can do some amount of imitation learning on existing gaits and things like that to seed the optimization. But once you get into that basin of attraction, pure RL can really go a long way these days. And so that's been really
climbing, keep getting better.
Yeah, and it's been super impressive, some of the results that research labs and different parts of the industry have been able to show off with just really, really impressive dynamic motions.
Yeah, I guess, it just seems like our whole industry has learned more compute better And it like is very true, which is just crazy.
I think
for this kind of
we're
thing.
seeing the same trend that's hit many other areas before us, right? Which is just that there's a lot of things that that we were trying to solve, by changing the problem, and it turns out that we can just change our cluster size and solve it instead.
Yeah, very much. It's so exciting and also a little disheartening to me for some reason, which is kind of funny because it's like you learn all these advanced things and then it's like, just simulate it more and it works fine.
Well,
which
I think there's a balance there. There's
Yes, of
definitely
course.
learning structurally about like the techniques that work, and those work at any scale and are really important.
Yes.
But then there's also the stuff where, like I did this, in my PhD at Carnegie Mellon, I was doing a bunch of simulation with multi-agent, I think it was like DEC POM-DPs, which is partially observable Markov decision processes, and then decentralized versions of those where they're spread across machines. But now I don't know that I would have to do any of that because I could easily probably do that same optimization on a single machine, and therefore I wouldn't have had to do nearly as much work as I was doing to solve these decentralized policies, because I wouldn't need them to be decentralized really. So there's definitely this evolution of like the techniques that we needed to do back then. A large portion of what we were solving for was actually just trying to work around limitations of things like compute and distribution of information. And nowadays, some of those problems have been solved, and some of them are still fundamental problems and benefit from these techniques.
Very true. Yes, for sure. Okay, so higher blocks, you're saying.
Yeah.
So we have
all right. Let's
lowest
we
level
start
control
at block number one.
Yeah.
So block number two above that is the skill layer. So the controls block again is I am getting some input of like, I need to modify my environment somehow. I need to exert forces or do something. Let me figure out how to do that at the joint level. A layer above that is, what am I trying to do? Like some task specification. And then what does that mean I should be doing with my environment? So I need to pick up a tote. The tote's over here. Maybe I like draw a mask over it in an image or something like that, or I give it a pose or something. Now I need some layer that's, again, pretty close to the robot, because it's got to take into account changing perception information, but maybe not as fast, right? So maybe 10 hertz or 30 hertz. And it's going to take that and generate out a new, what should I be doing with my environment? I should be putting my hands here. I should be grabbing it like this. I should be exerting these types of forces. I don't know all the way how that's going to end up being joint level controls, but that's what I'm trying to do with the world. So we find that that's like a useful layer to sort of separate out and be training, is this idea of a skill, which is some sort of task specification down to some sort of a specification of what needs to happen in the environment.
Yeah. Okay. And then how are you benefiting from AI with that?
Well, that's an area where historically you would get someone to do, and we still have quite a few very talented folks here who write out that specification in something like Python. It's maybe, hey, if you see the tote here, move to this location, push the hands against it, close the fingers, pick it up, and then that's, the pick up tote primitive, right? And we had to hand author those blocks, and you might make a block for picking up a tote and placing a tote and moving between areas. And skilled humans would write those, right? And still do for a lot of the more complex tasks. The interesting piece with the newer AI technologies, especially around things like behavior cloning, is that you can do learning from demonstration or imitation learning, or even doing things like RL to solve for how to do that layer of the stack. How do I get this task done by modifying something in my environment? And so that's new. And because that has always been a large chunk of building out the capability of a robot, we're now in this space where, hey, the thing that was the most expensive sort of incremental cost of going into a new environment is now working a totally different way. Yeah, it's operating under a totally different model.
Went to 10% effort instead of 90 or something like that.
Yeah, and just the type of data that you collect, the type of person that can be collecting data. So if you're talking about collecting something like teleop data, right, you might be looking at someone who's a technician collecting that data rather than someone who is a software engineer, right? And so that lets you, definitely move more quickly in building out these skill sets. And then your software engineers are more dealing with the infrastructure behind it rather than tuning each specific skill that you have to build out. So that's a huge game changer. And I think that everyone is scrambling to figure out how well and what the right techniques are for this part of the space. This is the really exciting, oh my gosh, this could really change,
open up a lot of things.
Yeah, how robots are scaling into environments. And so we're really interested in this. Third parties that, like Physical Intelligence and Skilled are really interested in solving for just the model part of it. But everybody is scrambling to figure out how this is going to be a game changer.
Do you think that, so I mean, one of the things that we've been hearing for the last, 20 years or something is like data is gold for all of this. And it seems to be true with all of the processes that require a lot of compute. Do you think that we could enter a data is cheap point of view when it's like, oh, you just need to show it once and it learns how to do it? And then for a lot of applications, it's like the companies that have been collecting an endless amount of data, they're not really sitting on a mountain of gold like they thought for this kind of thing. Do you think we could enter that? Or is it a silly idea? Or what are you thinking?
I think it's somewhere in the middle, maybe. So in order to get to models that do really well with a little bit of data, they tend to have to be pre-trained on a lot of data. And so you end up with this situation where, depending on where those models are coming from and how those are commoditized, you may end up in a space where a little data is all you need, or you may end up in a space where you need to collect a lot of data to build out that model that lets you then move from point to point with a much smaller amount of data. And I think one of the big differences here is that in physical intelligence, in physical AI, as the terminology has become known, physical AI doesn't have this long-standing corpus of really well-curated data for the types of robot platforms that we're creating today. If anything, the largest data sets are probably single-arm overhead tabletop problems coming out of academia, or some of historically the largest data sets. And so now we're seeing a lot of folks scramble to build up these data sets and build models off of them. But it's pretty different because we can't just go and basically download the entirety of everything that's on Wikipedia. Some folks are trying to figure out if maybe we can use some portion of the videos on YouTube. Maybe that's a large corpus we could unlock with the right transformation. But that's right now a huge difference between where we are with LLMs and VLMs that are working in kind of just abstract human reasoning and human language to systems and models that are dealing with physical effects of the world, spaces. Right? And there's a lot of differences in the data sets that people have available and how well curated they are, and the types of robots and sensors that have been used to collect the data, and how that affects how well it works on other systems and how well it transfers. So I think we're going to see some amount of perhaps commoditization of parts of models there. So it may be the case that there become established players that produce good models that other people can basically fine-tune to their applications with very small amounts of data. It could be the case that a really big entity like an NVIDIA puts out an open source model that sort of levels the playing field in this space.
That would be like amazing.
Yeah, and they're certainly working on it with efforts like Groot, right? That is the intent of efforts like that, is to basically try and produce models that sort of level the playing field. Because of course, for NVIDIA, the more people that are playing, the better they're doing, right? Because they're able to sell to all of them, right? Exactly. So we could see that happen in the space. I don't think we really know exactly where it's going to land, but I think what we're seeing is that at the very least, we have the amount of data where we can get single skills or like small generalized skills in certain local areas to work really well and really reliably. And so we know that at the very least seems tractable, and that seems like it would work. And that alone is already a pretty big unlock.
Oh yeah. Okay, so then above the skill level, I suppose you have something like a planning level or something like that?
Pretty much. At that point, you start getting into, what you might call a cognition or reasoning level. And that's really where VLMs and LLMs
are amazing.
Are really probably. Just, they're right there. At this level, you're basically starting to think agentic AI, where your skill is the API that you're interacting with. And so here, you're really just leveraging web scale models. You don't necessarily really need to build anything that's too
No,
specific.
I didn't really have questions on this one. This one was kind of clear.
Yeah.
Yeah.
The really interesting part, though, that I find particularly exciting is that because the space is so exciting to so many people, you really see really large players spending time making models that are specific to physical systems. So Gemini, for example, Google's been training on robot data sets, which makes VLMs that, their versions of Gemini that are actually able to answer or better answer queries that pertain to things like objects in the world, right? So historically, it was really hard to ask a VLM for things like, hey, what's the object that's, to the left of my hand? Or like, what would I need to do to go pick up this object in the back of the scene or behind the table and move it to close to me? Like, it did really poorly around egocentric reasoning and, relative reasoning about things in the scene. But now, because so many people are applying these VLMs to physical applications, that's now a specific area of focus that the providers are tuning towards and trying to collect data and correct for.
So cool. Wow. Okay, yeah, what a thing. It's amazing. All of this feels like it's moving so fast for all of this, where it's like, I have no idea where we'll be. Like, even like you think back to 2020 and where the state of robotics was, because that to me feels like a big indicator in time because of COVID and everything. It's like where we were then. It's like everything has, like, now we have this whole AI boom and everything. And now there's all this interest in humanoids. And it's so interesting where everything is going.
Yeah, I think that's the most exciting part about all of it, is that regardless of what the specific outcomes are or exactly what the robots of the future look like, what's increasingly clear is that we can have them.
Yeah. Super cool. So going back to agility, where are you guys headed? I know it's hard because, like, okay, we think back 5 years and everything has changed. Where are you guys heading in the next, like, 2 to 5 years, say?
Yeah. So for us,
I'm sure the standard and unstructured environment, or less, I don't know, less work cell environments, but
yeah,
where are you going otherwise?
Well, I think the biggest thing for us is building out our V5 platform to really be the platform that we can scale out of the work cell with. That's really what we think is a gating function to there being a lot of robots out there doing a lot of different tasks. We can already, we already have a fleet management system. We can already deploy new over-the-air updates to the robot and give them new capabilities out in the field. They don't require a huge amount of customization for different specialty tasks currently, right? We don't do that. We only build one platform, and it's called Digit, right? So from that perspective, that's all ready to go. And so if we could just get these last few unlocks around things like the safety, around things like, opening up our manipulation capabilities with the tool changer, we're really trying to unlock these last few pieces to kind of open the floodgates for all the stuff that we've been working on that's almost ready to be unlocked, right? All of the capabilities we've been developing. So for us, that 2 to 5 year timeline is really a scaling timeline. It's get these last few pieces unlocked and then just open the floodgates. And so we hope that's what our next 2 to 5 years look like. We hope that we are going to be out there in the world, that Digits will be doing lots of different tasks, that they'll be easy to deploy, that they'll be out working full shifts in the places that we can deploy them now from a regulatory standpoint. And then that will basically be the driving function for other industries to want it, right? They'll see them, and that'll become kind of a fire that gets lit to say, hey, I want these in my stores, in my facilities, in my use cases. And that'll help really drive the ecosystem to scale further.
Yeah, it'll be a flywheel. It'll be spun up at that point. That'll be nuts. So wrapping up, what do you hope that our listeners and watchers take away from this? Or do you have any calls to action, like you guys are hiring or anything else that you'd like to wrap up with?
Yeah. So certainly, yeah, if you see open roles, we're always looking for talent. We definitely, if any listeners are interested, I encourage you to go take a look at our jobs postings. I would say if you are a humanoid robotics provider yourself, I would encourage you to understand safety and start, working with the standards bodies that are working on that. If you want to join our ISO working group, I believe it's 25785-1. You can get involved, get informed at least, right? Don't get stuck where you build a perfectly working robot and you can't legally deploy it anywhere. Like
That'd be crazy.
Exactly. Like don't end up there. Everybody should be up to date on this stuff. Everybody should really understand more, I think, about what it takes to safely deploy robots in production and at scale, because I feel like it's something that I certainly didn't even think about when I was in academia. I didn't even know most of these standards existed. And it's been such a core theme of what I've had to do to take robots to production since then in my professional career. So I think that's, if you're a roboticist and you don't know what safety standards are, or like which ones are applicable, like go read up on them, go learn about them more, because they could play a big role if you ever try to build a robot as a product.
Hell yeah. How do you learn up on those?
Well,
what would you recommend?
Yeah, I mean, I would recommend doing some reading on a field called functional safety, and also maybe starting with, there's a lot of good primers on safety for industrial robots. It's a field that's existed for a long time. And even just seeing what that looks like and what the standards are and what they mean for different types of robots is I think a useful thing. Just knowing that they exist, and maybe just ask the question of, hey, I was thinking about using a robot in X environment. Like, what standards apply in that environment? What would I have to certify my robot to? Even just starting that thought process. And then once you really get into it, there's third parties that can help you with that. And there's certainly a lot more knowledge that's available. But I think it's just something that's not necessarily on everyone's radar. Like, every robot should have an e-stop that you can get to stop the robot. Like, if you don't have one, put one in, and make sure that if the robot starts going haywire, you could actually get to it, right? Stuff like that, right? So I think that's important and not always on everyone's radar until something happens, and then it's on their radar.
Yes, big on their radar.
Yeah, but I think this is an exciting time. Safety is a huge component of this. I also think that, if there's still any AI naysayers out there, like, all three of you, like, come on, guys, like, get on the train, right? This is happening, right? It's not a question of if, it's just a question of how much and how fast. And really, I came from the position of doing a lot of classical AI, so more like optimization and search type strategies in the past. And over the past 3 or 4 years, I've really had an eye-opening experience of just understanding, how much is different and how much capability and flexibility is available in the latest generation of AI model building systems and simulation and training platforms. So if you're not thinking about that, that's also definitely something that's worth trying to, although that field moves so fast that like every 3 months, like, you have to relearn half of it. But
I know.
At least start to keep your finger on the pulse, and don't assume that something won't get solved, because they almost categorically end up being solved very soon after you say that.
I know. And how would you keep your finger on the pulse of AI? Because that to me, it's like, I don't know, like, I don't really have a good way other than talking to great people. Yeah.
Well, I do think that's a core part of it is, pick a few sources of folks that, are good, knowledgeable sources that can parse through the information. So actually, one of the things that I do personally is one of our lead AI engineers, Chris Paxton, runs a really active social media presence, and so I'm often following
he's
him.
Excellent.
Yeah, and I think following him, Jim Fan at NVIDIA and other folks like that. So that's how I get a lot of my news, is by seeing what they're responding to and their assessments of different work that's coming out. I rely a lot on that to get kind of a filtered feed, because you're right, it is a fire hose if you're just trying to look at every.
Yeah, and there's so much hype, and there's so much, because I mean, like, there's a lot of promise, but there's definitely a lot of hype also. And so having great folks like Chris filter it out Seems like a good thing. All right. Hell yeah. Well, Pras, this has been a lot of fun. Really cool to hear what you guys are doing, and that sounds really promising.
Thanks. I mean, this is just a really exciting time to be doing this type of robot, to be doing this type of work. So, it is really awesome to just come into the lab and just digits off picking groceries or putting Halloween candy in a basket. And we're just like, oh, that's
So
just
cool.
That's just what we're doing today. Like, great.
Super cool. Hell yeah. All right. Thank you, Pras.
Yeah. Thanks so much for having me. Bye.
Bye, everyone.